All right, I am Karen Gundy-Burlett. I'm the program manager for the NAMS-2 contract, and I would like to welcome you to today's edition of Airtime by NAMS-2. And this is presented by Crown Innovations in collaboration with UC Berkeley's Citrus and Banatao Institutes. And this is a series of seminars on advanced aviation, interesting research, and innovative methodologies in AAM and air traffic management. Our speaker today, Mark Mueller, is from UC Berkeley, where he leads the High Performance Robotics Laboratory, where research focuses on design and autonomy of aircraft. Dr. Mueller received a mechanical and aeronautical engineering degrees from the University of Pretoria and master's and doctorate from ETH Zurich. Dr. Mueller is the lead inventor on multiple commercially used patents, and currently serves as the Associate Faculty Director of the Aerospace Programs at Berkeley. The title today is Designing Aircraft for Autonomy. Dr. Mueller.
Excellent. Well, thank you very much for the opportunity. Thank you for the organizational effort you guys have put in. It is a pleasure to get to give the seminar. I apologize for not being in person. Unfortunately, somehow my this semester is just got meetings everywhere, and driving down is just very challenging. So we kind of compromised on this spot where at least I can make the virtual seminar work. So I'm grateful for the opportunity. My background is mostly in robotics and flying robotics specifically, and I've become very interested in generally AAM and how we can think about designing these systems. And what I want to talk about today is specifically how do we design aircraft with a view towards autonomy, right? So with autonomy baked in as early as possible. Now, as all of us here, I suppose we're living in the Bay Area and we are living in the future. So if you go to downtown San Francisco, you can get into a robot taxi that'll drive you around the city. For some of them, you even get to pay nowadays. It's a commercial operation. I don't know if they're making a profit yet, but certainly they have revenue. And it's become very normal, right? So we're very used to autonomy in these aspects. And at the same time, we see this sort of promise of autonomy in the air, or at least sort of new modes of transporting people through our cities, which might unlock faster commutes, better, higher quality of life fundamentally. And of course, to unlock this sort of autonomy is important, and autonomy in flight has become also fairly commonplace to us. So when we look around us, we see the sort of commercial drones that you might purchase and get for Christmas, DJIs or these Skydios from the Bay Area, but we also see sort of autonomous aircraft being used for other exciting use cases. A favorite of mine is Zipline, that has used these aircraft for delivering blood in Rwanda. So you have sort of a centralized blood service, and then if a hospital, maybe there's a car accident, needs urgently a certain type of blood, you can dispatch this very quickly and very efficiently using these aircraft through what would otherwise be a very complicated road network through the rugged terrain of Rwanda. But you can do this in flight very quickly, and autonomy is key to be able to make this commercially viable, and also just to be able to get the sort of scale of operation you need for such a complex system. At the same time, we all want to have our packages delivered by drone. We all have, 2-day shipping, and we think this is not fast enough. So this promise of being able to do, logistics through the air is also very enticing, right? And it has all sorts of potential benefits, like reducing congestion on the road, reducing accidents on the road, and just being able to move things faster and thereby reducing overall costs. And I look at all of these systems and we see, there's a lot of exciting things happening. And I am interested in how we design such systems. How do we create these systems in the first place? And when you think about especially these flying systems, they have many competing objectives. So for example, if you want to design some sort of air taxi, you want to create a system that is quiet, that is autonomous, and that is safe. And why quiet, autonomous, and safe? Well, quiet you want because this needs to somehow be politically palatable. And if your neighbor every morning takes off in what sounds like a jet fighter, you will very quickly have local ordinances that make these systems impossible. You want it to be autonomous because to achieve scale with these, you cannot rely on human operators that are skilled. You want these systems to be usable without the expert operator. And of course, they have to be safe. Anything like this we want to deploy at scale needs to be safe to use. Now, a classical approach for how one might go about creating such a system is, to have you have one office down the hall, and in that office sits Alice. Alice does the mechanical design. She builds the system, and then she hands it off to Bob, who sits in the office next door. And then Bob is tasked with making it autonomous, designing the control system for this. This is sort of the classical divide and conquer approach we do in engineering. But the problem with these highly integrated, highly constrained systems is that this tends to be very suboptimal potentially, or even impossible to do well. So what we're interested in is, how do I simultaneously think about the controls, the autonomy, and the mechanical design? And specifically, how do I use controls theory as a lens through which to view the design problem? And this little cartoon here, this is just sort of my diagram of what I get excited about when I do research. So I'm interested in systems that have interesting dynamics, so things where speed matters, where I have to think about forces, things like this, where autonomy is important, so where there's some aspect of feedback control, and of course where there's design degrees of freedom, right? So where you actually have the freedom to think about how you're creating the system or the aircraft or whatever it is you're working on. And the more of this overlaps, just the more interesting it gets. So what I want to talk about today is focus heavily on the design aspect of this and thinking about how we can create and design systems with an eye towards autonomy. I think in about a month, I get another opportunity to talk at one of these seminars where we will talk a little bit more about our planning work. So that's a little less on the design side and a little bit more on the control side for how we can think about motion planning. I want to talk about 3 specific examples, and then depending on how fast I end up talking, maybe a 4th one that I can talk a little bit about as well. But the 3 main ideas I want to talk about are 3 specific research projects that I think sort of maybe illustrate a little bit about how we think about this interaction. On the one hand, some automated design where we can create closed loop designs without having to go through a lot of engineering effort necessarily in the loop. A second example, which is a particular case where we try to design a system which can exploit angular momentum for more robustness to disturbances. And then a slightly more out there idea about how we can create a system that is more energy autonomous. So how we can sort of release ourselves from the problems of energy density that we have when we're doing electric flight. Let's first look at this first example when we are interested in automating closed loop design. So this is motivated by sort of very practical sort of robotics use case. This is mostly illustrative. I think it doesn't really constrain too much the end result algorithm, but it gives us a concrete way of thinking through the problem. This is motivated by working on construction sites where maybe you want to carry certain goods, right? So payloads through the construction site from point A to point B. Classically, we would do this with either a crane if there's, the sky above everything is clear, or if that's not clear, it would basically be some folks with, hard hats carrying stuff around on wheelbarrows or carrying it around by hand. Question is, how can we unlock the sort of third dimension to allow us to do this robotically and move these things quickly from point A to point B, perhaps allowing us to more, quickly construct things and move things around. The goal is to carry sort of objects, relatively large objects that are going to be oddly shaped, and I'm going to carry them by attaching to them basically drones. So you can imagine I'm going to have these drones, I'm going to call these lifting units in the context of the segment. I'm going to attach these lifting units to this object I'm trying to carry, and then this will allow me to carry the object from point A to point B. We are specifically here considering rigid attachment, so I'm rigidly attaching the lifting agents to the payload. Of course, you might consider doing something where the payload is slung, but then your system entirely gets a lot larger. So here we're looking at a compact system. So we're just going to attach the agents rigidly to the objects. We want the system to be, in this context, safe. And what I mean by safe here is kind of narrow. I mean it's very robust to perturbation. So as you're flying from point A to point B, and as maybe there's wind disturbances and sensor noise, etc., this system should be very robust to this, so it can able to hold its position well, operate in narrow environments, etc. The problem we can then sort of narrow down to something mathematically tractable. The way we do this is we assume that we know the characteristics of our payload. So we know the mass characteristics, we know the geometry of the payload, and we're going to attach our lifting agents, in other words, these drones, on some perimeter of the object. So we know that there's sort of some outside perimeter of the object to which we're going to attach our lifting agents. And the question is, where should I attach these agents to optimize for robustness? So you can imagine if you decide you want to carry this payload and you're going to attach 4 drones to it, you have this perimeter, which in this case is sort of this polytope. Where on this polytope should I attach these agents to have good robustness? And what I want to do here is not do this in this phased approach where one person does the mechanical layout and then I pass it to the next person to do the controls design. Because what I want is I want the best mechanical layout, which should not be confounded by varying qualities of controls design, right? So we want the controls design sort of implicit in the design loop so that we can really design for closed loop characteristics. And this is as opposed to sort of, I think, the classical approach where you design the mechanical system for open loop capabilities. Think of something like thrust to weight characteristic, and then after you are done with that, you pass it on to the next office where the person then does the closed loop design for the system. How we think about this is as follows. So after you have attached these lifting agents to your payload, it becomes a single 6 degree of freedom rigid body with equations of motion, something like this, right? So you attach your lifting agents to the body, and then as a function of where you attach that, you will have the linear translational dynamics, the mass times acceleration, the forces here we model as weight, and then the total thrust from your lifting agents, which I just wrote as T sigma, which are pointed in this direction, R being a rotation matrix, E3 being the thrust direction of the vehicle, and then FD being the external disturbance force that we would like to be robust against. And you have the angular mechanics, right, which has to do with the rate of change of angular velocity, angular momentum terms, and then the torques that we can produce, tau, and then the external disturbance torque, tau d. Generating these equations of motion is, of course, fairly straightforward. As you change the mechanical layout, these equations of motions change by changing the mass distribution. So as you change where these lifting agents are massive, so it changes the inertia matrix. So both by changing the center of mass of my total system, as well as just changing how the mass is distributed. It also changes the moment arm. So if you imagine this agent producing a force, the moment that this force produces, this torque here, will be a function of where I attach the agent. And it will, of course, affect the forces required at equilibrium. So different layouts will have different equilibrium force conditions. So I can solve this parametrically in terms of these angles. And then we can ask the question, how do I think about those angles, these design parameters, to design or to create a good closed loop system? The way we do this is through a first order analysis. So we define the equilibrium, which we can calculate using fairly straightforward techniques. This equilibrium will be a function of these design parameters. We can linearize the equilibrium, we can linearize the dynamics around the equilibrium. That will give me a linear function where my matrices are, of course, functions of those design parameters. So for example, as you change the mass distribution, you will get different dynamics A and B matrices, this being the classical rate of change of system state proportional to somehow the system state itself, the input we generate, and then the disturbance that we have. And what's important to note here is as you change the parameters, you're also changing the gain of the disturbance, right? So as the inertia changes, an external force or moment will have a different effect on the system dynamics as well. This linear system, I can then design a controller for. The way we will do this here is we will design a linear quadratic regulator, and I'll talk a bit in a moment for why this is the choice we would like to use. But if you allow me to use a linear quadratic regulator and you give me these functions that generate the matrices from the design parameters, I can calculate the optimal feedback gain K, and I can calculate the closed loop input as the equilibrium input U bar, plus this perturbation, right? Plus the feedback that I would need to produce to control the system to the equilibrium. Now, in this linear model, the disturbance acting on the system is uncertain, so it is random. which means that the state is random. And since the state is random, the feedback control is random, which means that my input to the system is random, or in other words, it is stochastic. And we can then analyze this stochastic input to reason about the quality of our design, right? So this allows me to sort of reason about how does the design parameter theta affect the quality of the input that I then have to send the system. How do we use this? So if I assume that the disturbance follows a normal distribution, right, so zero mean with some variance that we assume, I can solve the distribution of the inputs that I actually generate to the system, and this will also be some normal distribution, which will be centered at the feed-forward term. That's the equilibrium force that I need to produce. And that will have a variance ellipsoid, which will be somehow proportional to this feedback gain multiplied by the variance of the state due to the disturbance. Now, each agent and each input that I have is bounded. So we're going to think about the bounds as that thing, the input bounds as that thing which denotes danger. So I want to have the system able to operate without hitting an input saturation. So since the noise is normal, it has infinite tails, thus the forces that I would require from this linear feedback gain will also potentially go unbounded in both directions. And I can calculate the probability that the feedback control input that I require exceeds the saturation limits of my actuators. And this is sort of schematically drawn here. If you imagine each actuator I have has a lower and an upper bound on the control effort that we can get, here shown for 2 actuators. But of course, in practice, this is some much larger space, and you're dealing with like a cube or an object in a much higher dimension than 2 dimensions. In 2 dimensions, you have the feasible input space being this gray rectangle. You have your feed-forward equilibrium input from the system being somewhere, hopefully, within that rectangle. And then you can draw the confidence ellipsoids for certain standard deviations. So you can sort of imagine these, the Mahalanobis distance, 3 sigma ellipsoid might look something like this. We then calculate for a given mechanical layout and a given then optimal feedback control policy these ellipsoids, and can then calculate what is the closest actuator violation of the actuator limits in this probabilistic space. And this gives us now an optimization program where our cost function is how close we are to hitting a saturation, and we can then vary the layout parameters to minimize the likelihood of a saturation, or alternatively maximize the distance from the inputs we give to a saturation value. That distance interpreted in the stochastic sense, right? So the standard deviations until you hit saturation. And the idea is, if I do this, it gives me a way of mapping from the complex design space to a single scalar, that scalar being, the number of standard deviations I am away from the closest input saturation. And if I have a more robust system, or rather, if I have a system which is less likely to hit saturation, it is more robust, right? So it is less likely to get into trouble as it operates through the real world. This really boils down to H2 optimal control. So those of you for whom that is a concept, that's really the ideas we are exploiting here. It is this H2 robustness theory that allows us to do this linear analysis. If you do this, you get an optimization program. It is a nested optimization. It is not that heavy to compute for the kinds of systems we're dealing with here. So it'll maybe run a minute or so on our very unoptimized MATLAB code. But you can run it and you get a result. And I want to show you what this result looks like for 2 particular examples. The first example is kind of a boring example. Boring in the sense of you would know what to do without any of this theory that I just explained. So we're carrying a rectangular, or specifically a square payload. So this plywood square here. We're going to carry it with 4 agents. On the left-hand side in the video, you will see the optimal performance. So what is the system doing when I have the vehicles in the optimal layout? And on the right-hand side, you will see a comparison when the agents are in somehow a suboptimal configuration. So you can see for each agent where I attach it to the perimeter is my degree of freedom. On the left-hand side is the optimal configuration. On the right-hand side is some sort of arbitrary configuration. I say this is a boring example. Let me just explain before I show you the video. in the sense that the result that our tool spits out is put the 4 drones in the 4 corners, and you would have come up with the same idea without any of this. But this just validates that, one, your intuition is sort of giving you the right idea, but 2, that the tool actually does something useful. What you're seeing here is just the system task hovering, so doing station keeping, while under its own perturbations, right? So it's being perturbed here by just the airflow that it generates in this room that we are flying. And you can just visually see that the system on the left is much more robust to perturbations than the system on the right, right? So these sort of horizontal deviations are much smaller with the optimal layout. Okay, so that's the case where you didn't need any of this. Maybe a more interesting case is this payload here. So this payload here is shaped conceptually maybe a little bit like an M. It is, again, a plywood thing, and we're now going to carry it using 3 agents. So the program is tasked with solving the 3 positions of these agents on the payload. On the left-hand side, again, you have the optimal configuration that the tool spits out. On the right-hand side, you have the arbitrary or the non-optimal one here. It's not arbitrary at all. This is what I would have guessed. So if you had asked me to lay this out myself, I would have come up with this nice symmetric solution, as opposed to this asymmetric solution that the algorithm spits out. However, when we let it fly, we should see that, what's happening here is you see one of the graduate students coming with a perturbation. If we perturb the system, we see that it's much more robust with this optimal layout than with the suboptimal layout. The perturbation here is just a mass that we're attaching off-center. So think of it as a moment that we're applying to the system. And what is interesting here is that we can now design this layout problem with very little engineering input, right? Once I have defined the once I've defined the design degrees of freedom, where I want to attach these lifting agents, this tool allows me to trade off different mechanical designs without separately having to think through the control design problem, right? So really, I get to focus on the mechanical design almost in isolation, right? Almost solving the mechanical design, but getting a result that is optimal in closed loop, right? So that is from the design point, from the initial concept, is thinking about how do I make the system more autonomous? How do I design it so that the autonomy works well? Now, of course, here we are looking at a fairly constrained design problem. Let me stop this video loop. But nothing prevents us from taking some other design problem. Of course, these design variables need to be somehow continuous. So you can think of designing an air taxi style system where you're asking, where on the wing should I lay out the motors and propellers? And you can then solve this from the perspective of the control closed loop performance. You can search through the design space with this tool, running this optimization, and it will give you a design concept that is closed loop optimal. Now, of course, in practice, no design has got a single cost function. You're never only concerned with the controls cost. You're also, of course, concerned with, does it satisfy your landing constraints? Is it energy efficient? Does it look good? Whatever else. So in practice, of course, this is one tool of many that you would use as you explore the design space. But this should give you a fairly fast way of at least reasoning about the design trade-offs that you have in terms of the autonomy without having to do this 2-step design first, the mechanical system, and then design the control system. You can do this in one fell swoop, in one loop. Okay, the second example is a more narrow design example. We were specifically exploring the idea of exploiting angular momentum for disturbance rejection for an autonomous flying robot. So this was motivated by, I'm operating my system in complex weather, so maybe hailstorm, in large wind conditions, or whatever other perturbations there might be out there. And what I want the system to be able to operate safely and reliably in all of these conditions. Now, if we think about, these hovering systems, be that a multicopter here, or one of these hybrid systems where you're moving at low speeds and thus the wing is not relevant, the mechanics are fairly straightforward. You have the translational motion, the translational acceleration is a function of the weight of the system, of course, but then the thrust forces that I can produce all acting in some body fixed direction. and I have the angular mechanics. The angular mechanics is much more interesting. Typically, I have the rotation matrix evolving through the angular velocity, and then the angular velocity evolving according to this fun expression, which is, of course, the quadratic coupling of the angular velocity, and then the moments I produce through the forces. So these are the propeller moments, and then the disturbance acting on the system. So what we want to do is we want to design this system to be robust to perturbations. And when you look at this expression, you notice that the position of the aircraft is really dominated by the orientation of this aircraft. So as the vehicle is perturbed and your thrust direction is pushed to point in a direction different from maybe the vertical, you will have position deviation. So then this vehicle will accelerate horizontally and potentially downwards as well. So what I really need is I need the orientation of the system to be very tightly or very tightly controllable, right? So I want the system to have very tight pointing stiffness so that I can get the position to be safely within some bounds given disturbances acting on the system. Now, of course, one way you can do that is just build very large actuators, put those actuators very far from the center of mass, and you can get very large moments. Moments give you accelerations, angular accelerations, and then I can correct for disturbances by just having very stiff feedback. But of course, practically, there are constraints to this. Practically, I can only put, I can only afford motors of certain power. I can only afford a certain noise footprint, etc. So there's only so much I can do in terms of making the system more stiff by having better actuators or better feedback control. However, there's maybe a different way of thinking about this. What I would like to have is I would like to have stiffness about one body fixed direction, this thrust direction of the body. And if you think about a standard system, maybe going back to this, a standard multicopter style system is designed deliberately to have zero net angular momentum when you're stationary. And it's done this by having the motors in alternating pairs. So some motors rotate right-hand rule downwards, other motors rotate right-hand rule upwards. So if you sum the net angular momentum over this multi-body system, it sums to zero. However, if I can exploit angular momentum somehow, if I can generate a net angular momentum, I can use that net angular momentum effectively to create a stiffness for me. And we do this, and by we, I'm using the royal we, this is not me, this is other people, but we do this often in space where we have a similar important direction and we have the system have angular momentum around this direction, and that gives you sort of natural stiffness for this direction. That just follows from the mechanics of our aircraft, of our system. So the question is, can I do something similar for an aircraft? And the way we do this is sort of similar to how one might do this for a satellite, is we add a rotating component to the vehicle. So we take our aircraft and we attach to it a flywheel. That flywheel rotates relative to the aircraft, and this gives me an angular momentum. So if I write down the Euler's law of angular dynamics for the system, what changes compared to a normal system is I have sort of this multi-body mechanics term, which has to do with the acceleration of this flywheel. That's not so interesting, but what is more interesting is I, of course, have a quadratic term that has to do with the cross-coupling of the angular momentum from the flywheel with the angular velocity of the body. And we think here of our sort of design degree of freedom to some extent as the speed with which I will rotate this flywheel relative to the body. And this will be in the body fixed frame, this will be rotating around the thrust vector, right? So I want this angular momentum vector aligned with the thrust vector. What this does is it gives me a first order coupling in the attitude mechanics, right? So I get this quadratic term here. If you linearize this, you get a first order coupling, which is linear in the angular velocity of the body. I still have the same four control inputs, the same four forces that I generate externally. But now through this cross coupling, the attitude mechanics are just richer, right? So they're coupled with one another. How do I use this? If I do a linearization of the horizontal dynamics of the system. So this is a state space model of this aircraft where I'm looking only at the horizontal dynamics. So I'm ignoring the vertical dynamics just to make it slightly more compact. My state vector here, located on this side, contains the horizontal position, xy, the horizontal velocity, vx, vy, the Euler roll and pitch angles, and then the corresponding angular velocity components P and Q. And the linearized dynamics of this, right? So the vectored derivative is some matrix times the vector plus a matrix times my input torques around these two axes. And what I get through this angular dynamics cross-coupling is I get these two terms A bar. So for a normal aircraft without any net angular momentum, A bar would be 0, but for our aircraft, there is a non-zero term appearing in this matrix, where this non-zero term is a function of the inertia of the this flywheel that we have, the inertia of my aircraft, and the speed with which I rotate the flywheel. How is this useful? Well, it gives me, it modifies the dynamics, and by modifying the dynamics, it modifies the way disturbances act on the system. So what I can do is I can plot here on these graphs the disturbance sensitivity for the system in closed loop as a function of the speed with which I rotate the wheel. There are two graphs, so let me explain this slowly. The top graph shows the disturbance to the sensitivity to a torque disturbance. So this is a pure moment acting on the aircraft. The bottom graph shows the sensitivity to a force disturbance, so a pure force acting on the aircraft. And on the x-axis, we're varying the speed with which we're rotating that flywheel, or in other words, we're varying the amount of angular momentum that I store in the system. What we see is for this aircraft, if I normalize the sensitivity, so for a normal aircraft without any added angular momentum, the sensitivity is 1. So the gain from a disturbance torque to state error will be unity. As I increase the angular momentum, my sensitivity to a torque disturbance decreases, and it sort of monotonically decreases, which kind of makes sense. If you think about spinning a basketball on your finger, the faster you spin the basketball, the less sensitive this basketball is to a torque disturbance trying to tip it over. However, the force disturbance kind of has a more interesting property. It's slightly decreasing, but more or less flat for some range of angular momentum, but then the sensitivity starts to increase. Why is this happening? Intuitively, it makes some amount of sense. If you imagine a system with a lot of angular momentum, if you perturb it so that it moves to the side for this vehicle to come back to its original position, it needs to rotate its thrust vector to accelerate. And if there's a lot of angular momentum, you just need to do more work to rotate that thrust vector. So this is this effect that we see here. As the force pushes you off where you want to be, it becomes harder for you actually to control the system back to where you wanted it to go. However, there's this sort of sweet spot. There's the sweet spot where adding angular momentum reduces your sensitivity to moments and at least does not increase your sensitivity to forces significantly. So there's an opportunity to create more robust systems. And we then went ahead and experimentally did this, and this experiment sort of validates this idea. So what you're going to see in this video is this aircraft. It is hovering in our space. On the arm facing the camera to the right here, we have a little metal extension. And what we're going to do is we're going to drop a steel ball from a fixed height onto this metal extension, and we're going to see how the vehicle responds. This first video will be the response of the vehicle when there is no angular momentum. So there's a flywheel here, but that flywheel is not rotating. So we drop the payload, or we drop this steel mass on. This gives me this torque impulse, and we see the vehicle pitch over, the thrust vector no longer vertical. That causes me to lose height as well as accelerate horizontally, and this vehicle then proceeds to crash. Okay. I can then compare this to the vehicle with the angular momentum. So this video on the left-hand side will show the vehicle with the angular momentum, so with the flywheel spinning, and on the right-hand side without the flywheel. So this right-hand video is the video that you've just seen before. Sorry, the opposite. Let me just got that wrong. On the left is the video you saw before without the flywheel. On the right is with the angular momentum added. Let's first focus on the top video just to see the response. Okay, so we notice after this torque impulse, you see this sort of wobble, this precession motion, as you kind of might intuitively expect, and the vehicle can recover pretty quickly from this perturbation. These bottom graphs show the motor forces that we are producing to control the vehicle, and I'm showing this explicitly to convince you that the difference between these two responses is not that the one system has more control authority. The system on the left is fully saturating the forces as it is trying to respond. So it is also using all control authority that's available to it. What is happening here is just we are modifying the physics of the system to make this problem easier, right? So by effectively modifying the physics to make the system easier to control. We also did some analysis as we vary the size. Oh, sorry, this is noise. If the noise is being transmitted, this is a small vehicle where we do the same, where we can show with the payload, with the angular momentum as we drop the perturbation, we can show the same improvement in robustness. And again, if you look at the forces, you hopefully agree with me that this is not because the one system has more control authority. This is somehow just fundamentally different behavior. Okay, my last example, or looking at the time, probably my last example, is asking about designing for energy autonomy. So before we were thinking of autonomy through this lens of feedback and disturbance rejection, robustness, but there's a different aspect to autonomy, which is just the ability to operate without having to, replace or replenish your energy. And of course, for all of these systems, whenever you're flying, really, energy is one of your primary considerations. And especially when you think about these battery electric systems, the specific energy of batteries is just such that you're always extremely constrained by what you can do with the amount of energy you can fly, right? With the weight that I can carry and how that affects my energy. So if you explore this a little bit, and I want to sort of walk you through our thinking and then the system that, I think is one way to cheat in this problem. So if we think about the powertrain for typical battery electric aircraft, you have your battery. The battery, of course, stores the energy chemically. It can then generate electric power. The electric power is sent to the electronic speed controllers. This is what generates from the DC power that the battery generates, the AC power that actually drives the motors. The motors are connected mechanically through the shaft to some propellers, and then the propellers push the air around. And by pushing the air around, of course, I generate thrust. Now, if I want to think about energy efficiency, of course, I need to think about this whole chain, right? So I need to think about how efficient the batteries are, the speed, the conversion from DC to AC, the motors, the losses in the motors, etc. I am going to ignore this initial aspect of the powertrain just because this is fairly well understood, and typically you buy these things from a catalog, and hopefully you buy sort of efficient components from a catalog. I want to look at the right-hand side of this expression. I want to think about the efficiency and how the aerodynamics of propellers dominate power consumption, and how I can modify my design to think about this aspect of power consumption. With the sort of idea that if I design an efficient powertrain up to here, and I design an efficient powertrain on the right-hand side, this will give me an efficient vehicle. Now, propellers are complicated, and I'm a simple man, so I like simple models. So a very simple model of a propeller is this actuator disk model. The actuator disk model effectively takes the complexity of a rotating wing and replaces it with a magic infinitesimally thin disk that does not consider any rotation, but that adds energy to the fluid as it passes through the disk, thereby causing the air to accelerate and this causing thrust. If you do this actuator disk model, you get a very nice model for the power consumption of a propeller. This power consumption is proportional to the force that the propeller produces to the power 3/2, and inversely proportional to the radius of the propeller. Now, if I want to have long duration flights, what I need the propellers to produce either, or ideally both, a low force, so that this top term is small, and I want the propellers to be large, so the radius here is big, and this will give me low power consumption, and that means that the battery I have will allow me to fly for a longer time. Now, of course, looking at this expression, there's only so much I can do. The size of the propellers is really dominates rather the size of the vehicle, and this is typically fixed by some vehicle size specification. So I have a certain amount of size in which I need to be able to land my aircraft, and that will give me a radius that I can design for, right? So I'm fixed in terms of the size of the system I can do. If I think about the force, how much thrust a propeller produces, this really is dominated by the weight of the aircraft. And the weight of the aircraft is the mass, and the mass comes from the payload that I'm carrying, maybe passengers, maybe cargo, maybe sort of packages, whatever it is. There will be the structural mass, there will be the powertrain mass, and then there will be the energy storage. Now, to some extent, I can't do very much about the payload that's defined by the mission. The structure and the powertrain will be fairly fixed as well, right? So once you sort of decide an amount of power you want to generate, you will give you the powertrain, and then your structure will be whatever is required to hold all of this together in a sufficiently stiff and safe manner. But I can potentially think about changing the amount of energy I carry with me. I can change how much energy I store in the battery. Now, if you think about the energy in the battery as scaling with the mass of the battery, so for a fixed specific energy of the battery technology, the time of flight that I can achieve with my aircraft will be the energy that I can store in the battery divided by the power consumption of my system. The energy in the battery I will model as being proportional to the mass of the battery, and the power in the system I will model as being proportional to the force to the power 1/2 and inversely proportional to the radius, right? So this gives me that the flight will scale in this way, and what I can then do is replace the force with something proportional to the weight, and the weight I will model as the mass of the battery and the mass of everything else. And this gives me sort of a very simple relationship that tells me how the flight time is affected by changing the mass of the battery that I carry on board electric aircraft. And what you notice here is, of course, that this is not as simple as add more battery and then you will fly longer. That logic sort of pans out for electric cars, but does not work for electric aircraft. So if you make a graph of mass of the system versus flight time that you can achieve, where this is normalized, so a unit mass means that I don't have any battery on my system, and a battery mass of, or a normalized mass of 2 means that I have the same amount of battery on my aircraft as I have everything else on my aircraft. You can plot the flight time that you can achieve versus mass as this graph here. So on the y-axis, we have flight time, and on the x-axis, you have the total system mass. And we notice that there's sort of a clear optimum. So there's a maximum value of flight time that I could achieve with this aircraft, after which, if I try to add more battery, it actually reduces the achievable flight time. And a different way of thinking about this is, as I consume the battery, the mass of the battery does not reduce, right? And this is as opposed to combustion aircraft, where as you consume the fuel, your mass changes, so you're actually reducing the weight of the aircraft, thereby, potentially the efficiency changing through the flight. Here, your efficiency does not change as the battery reduces mass, as the battery reduces charge, so your mass is constant, so your efficiency is more or less constant as well. So since, if you look at this, you end up with the optimal design here being 2 units of battery for every 1 unit of anything else. So the optimal amount of battery is 2/3 of your total vehicle mass. This is unlikely to be a viable design, right? So you just end up with a system that will be extremely heavy, and you will have challenges with the structure of your aircraft. So where do you put the batteries? How do you make this thing stiff enough? And how do you make it safe? You'll end up with a very overspec'd drivetrain, in that you have to carry a very large mass compared to the mass of the payload that you're actually interested in. And of course, your overall system will be very massive. So you'll just have a lot of energy and momentum that you're flying. In other words, this will naturally be an unsafe, or at least potentially an unsafe aircraft that you're flying. So this suggests a sort of fundamental physical limit to what I can achieve if you fix the size of the aircraft payload you want to carry. So if you say I want to build an air taxi that can fit in a landing spot, maybe the size of 2 parking spots, right, and that has the payload of 1 passenger or 2 passengers, there's sort of a maximum flight time you can get from this, right? Which means there's a maximum range, and there's only so much you can do. You will never be able to exceed this. Now, when we're designing the system, there are all of these trade-offs I need to consider. There's the size, there's the range, there's the noise, and there's the safety. And these are constrained by what the size of the vehicle, etc. So there's an inherent tension here. So we came up with a way to cheat this problem, and we call this flying batteries. And the idea is I want to have a small aircraft that is low mass but capable of flying for a useful duration and a useful range. I'm going to do this by effectively doing mid-air recharging. So imagine you have your main vehicle, that's the large aircraft here, that's doing some useful mission. In this particular experiment, it's just hovering, but it could be flying from one point to another point. And I have this smaller flying battery that can come to the main aircraft, dock mid-flight, and effectively carry fresh batteries to the main aircraft. Okay, and what you see here is this sort of docking maneuver as we land And the flying battery is conceptually a large battery with some motors attached to it. What does this allow you to do? This allows you to effectively fly indefinitely. So this video here is an experiment where this drone here, the central drone, is doing an 80 minutes long flight. So don't worry, you won't have to sit through 80 minutes of video. But this aircraft is not capable of flying 80 minutes on its own, right? So by doing this mid-air refueling effectively, we can create a system that can fly potentially indefinitely. And we do this, of course, you have to do something that's at least not totally naive in terms of electrical interconnections, so you don't end up, overcurrenting the battery that's on the vehicle. But what this gives you is a main vehicle that can operate for very long durations with minimal complexity. And you can imagine as you're doing this, there's all sorts of complexity in the design space. You need to think about a mechanism that allows you to do this docking. You need to think about motion planning and feedback control that allows you to do this maneuver safely and reliably. But this now allows you to create a central vehicle that is capable of this extremely long duration mission, but it does so while being very low mass and small size. So if one of the audience is a venture capitalist with a few hundred millions to burn, what I would propose is creating an air taxi network where your air taxi is a very small agent capable of vertical takeoff and landing and maybe minimal amount of autonomous flight on its own battery, right? Just enough to satisfy the safety requirement. But then through your area of operation, through your downtown metro, San Francisco Bay Area you have a set of nodes from which these flying batteries can take off, meet you effectively mid-flight, and then allow you to consume not your own battery, which you are going to reserve for emergencies. So you have continuously a small overall mass. A small overall mass means that your system is inherently safer because you have lower momentum and energy in flight, but it also means that your noise load will be smaller, and specifically your size can remain small. And what this also allows you to do is as you are landing, you don't need to land with all of the energy that you need, or take off with all of the energy that you need for the mission. So your noise footprint will be much smaller as well. Now, of course, there are significant technical challenges. You need to somehow create a system where you can do this mid-air docking in a way that is safe and reliable. You need to do this with, the video here. Perhaps if you were a passenger on this aircraft, you would be slightly alarmed by this oscillation as the aerodynamic interactions of these aircraft interact with one another. But these are interesting research challenges that I think one can resolve with careful design of these systems. But in this way, we effectively get to work around the fundamental constraints of battery electric flight and create systems like this, which can unlock sort of usable air transport in a metro area without requiring very large aircraft, without requiring fundamentally new battery technology, while allowing us to maintain this sort of fundamental cleanness of battery electric and the reduced operational cost of battery electric, right? You don't need any of the maintenance of combustion, etc. Okay, with that, I will sort of acknowledge that I get to come and give these seminars and talk about all the cool stuff that we do. But of course, in the background, there's a bunch of very smart, very creative, and very hardworking students that do this work. The work I presented today is primarily of Carlo Bosio, Nathan Bucky, Karan Jain, and Jerry Tang, although it contains components of all of the various contributors in our lab, as you'll see in this recent photo. With funding specifically acknowledging NSF, the USDA, as well as Army Research Lab for some of this work. And so in conclusion, when I think about these systems and these problems, I like to think of controls design as, system design as controls design and vice versa. And when you're creating these systems, how can I cheat with physics? Like, how can I use the dynamics of the system to make the problem easier? And I think one of the key requirements to be able to do this is to view the design process holistically. So to be able to consider, as you're thinking about the mechanical layout of the aircraft, perhaps also consider the controls layout and the controls design simultaneously. And this allows you to both create better mechanical designs, but also better controls design. Right? So it allows you to have better systems in all directions. And then there's a feedback form here. I don't actually know where this QR form takes you. I didn't check it, but I was asked to put it on there. So if there is feedback, please use this form. And then there should be some time for questions, if there are questions. Thank you very much for the opportunity.
In the room? Are there questions online? I can't
see there's a
see.
question online. I'm just parsing it quickly. For short range or short duration mission size batteries, this means that batteries will be experiencing a very high C discharge, high C rate discharge. These tend to be heavier from a specific energy standpoint. This limits the utility of such a re-energizing approach. That's a good point. So my analysis assumes effectively infinite power that I can draw from these batteries. We're looking at the specific energy, not the specific power, but it is a good point. So as you change the specific power requirement, you also get somehow there is a trade-off in the specific energy as well. I have not done a detailed trade-off of this, so I don't know at what sizing will that be a fundamental limitation, but it is an interesting point. So as you sort of change the power requirement compared to the capacity, the C rate of the battery, you potentially will be modifying as well the specific power or the specific energy of the battery, and there will be sort of a second loop. My first instinct is that this will be a weaker interaction than the fundamental scaling, but I'm making that without actually having the data in front of me.
Is it mics open or?
Yeah.
Okay. Hey, Mark, this is Kapil Sheth. I had met you I think in April 23 when I came to present over there, and we had talked about this in-flight recharging, and we actually have published 2 papers, one with several different concepts for recharging, in-flight recharging. And the second one was more specific to this microwave recharging. So, you have a microwave beam and transmitter receiver and charge the vehicle that way. One question I had was for the battery recharging that you're doing with a battery drone, how complicated is the mechanism for recharging in the sense that the drone is already flying and it is using its own battery, and now you've got something else that comes in and starts charging it while the drone is still flying. So is there like a active and passive battery using mechanism that can be used, or how do you do it? How does the main drone do that?
Good question. So I'm probably going to get the details slightly wrong here. So in this particular video, we're not doing recharging yet. So this is just discharging all of the batteries with the idea that the battery on the main drone you're using for very little time. So your overall mission here is constrained by as we discharge the main battery. And the way we do this is we basically just have diodes that mean that the energy from the primary battery, so from the main vehicle's main battery, it cannot get recharged by accident, effectively, right? So you can't sort of have the high voltage from the new battery charge this. In a follow-on work, we did actually do the in-flight recharging as well. You can imagine here you're sort of playing a game where the main vehicle has its own battery. Whenever you don't have a docked flying battery, you're consuming this. So as your charge drops with these lithium ion, your voltage will drop. And then as your flying battery comes in, initially it has a higher voltage, so it can charge the main battery. And then, at some point, as we're discharging the secondary battery, so what the flying battery brings in, it will no longer have enough charge or not enough voltage to directly charge the main battery. But for us, this is, the way this mission is designed, that ends up not being a problem. So you have enough time to recharge the battery to compensate for that short amount of time where you are doing the battery swap effectively.
Yeah. Got it. Thank you.
And maybe here, sort of in designing the mechanism, this is a very naive docking mechanism. So we have a little cup basically that we land on, and the electric contacts are just sort of sprung loaded contacts that allows you to make the electric connection between these two systems.
Yeah, in our concept of a flying battery coming to charge, we pulled it in from below because some of the CFDs issues that were done, we found that if you have something coming from the top, then the perturbation to the main quadcopter was a lot more. And so, anyway, I guess these things I play with.
That's a good point. I think that analysis probably matches my intuition here. We did not, we designed it in this way because it's easier to get the docking just through the passive force, right, rather than having to actually sort of hold on to it. In terms of perturbations, if your objective is putting people on this agent, you probably don't like this the sort of instability that comes from the aerodynamics, and it'll be less when your vehicle is coming from the bottom. I will say that there's a lot of interesting questions, I think, about how you can do trajectory design to reduce this perturbation, to have this interaction be more steady, etc. as well. None of which we did. So this is a very naive implementation for the actual docking flights and feedback controller.
Excellent. Thank you.
Michael Abramson, online, you have a question?
This flying batteries, it's an intriguing idea, and I'm curious, would it be possible to implement battery swap in flight rather than charging them?
That's a good question. So in a way that would be more elegant, because now we are flying the battery, but we're also flying the whole powertrain that brought me that battery, right? And that's not useful when we're doing this. We did not really consider that in that much detail because the mechanism of doing a battery swap is much more involved, right? So you have to have something that can sort of pull the battery out and make an electric connection, then bring the battery back in, etc. So we did not consider that closely, but in a way, fundamentally, this might be a nicer system where you have this other agent come, it effectively swaps the batteries, and then it can leave so that your primary vehicle is not carrying the second powertrain for most of its flight, right? So that should give you a much more efficient overall design at the cost, of course, just of that mechanical complexity of the battery swap itself.
Thank you.
All right. Well, thank you so much, Dr. Mueller. That was a wonderful talk.
Thank you very much.
Yeah, next week our speaker will be Dr. Yasenka Rakas from UC Berkeley, and her title will be Predicting the Severity of Drone Intrusions into Controlled Airspace Using LLM and NLP Augmented Bayesian Interference. So thank you all so much, and we'll see you all next week.
Thank you.
All right.
Thank you.